Hello everybody, this is a lecture on the laws of thermodynamics. There's also going to be a brief discussion of entropy and refrigeration towards the end. So let's get started by just discussing what laws are in physics, or what physical laws are. They're really just really short, simple statements that accurately describe some phenomena in the universe. What's special about laws is that they're short, simple, and that they are true and universal. They haven't been disproven. There haven't been any counterexamples, at least within the realm of validity of the law. Now, that doesn't mean that the laws are always 100% universally true. They could be approximations of more of truer laws, like the law of conservation of mass, which used in chemistry was found to be not true when we do some nuclear physics. It's just an approximation of the more general law of conservation of energy. Newton's law of universal gravitation was found to be only approximately true when Einstein discovered general relativity later. But they're still laws because they haven't really been disproven, they're just good approximations. The laws of thermodynamics are four laws describing temperature, heat, entropy, and entropy. Einstein once said that classical thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown within the framework of applicability of its basic concepts. And part of that was because quantum physics and relativity were overturning a lot of classical physics. As I just mentioned, Einstein discovered relativity, which showed that Newton's law of universal gravitation was only approximately true. But scientists are very, very confident about the laws of thermodynamics being not just approximately true, 100% law. Okay, let's get started. The Zeroth Law of thermodynamics, it's called the Zeroth because it was actually discovered or stated after the first two. It says that if two systems are at the same time in thermal equilibrium with a third system, they're in thermal equilibrium with each other. So if B is in equilibrium with C, and A is in equilibrium with B, then A is in equilibrium with C. It basically says that any two things that are, anything that's at the same temperature is all at the same temperature. So it's kind of like a definition of how temperature works. The first law of thermodynamics we've already discussed, and it's usually stated as delta U equals Q minus W. The change in internal energy of a system is equal to the heat added to the system minus the work done by that thermodynamic system. And all it's really doing is accounting for the energy of the system. It's a statement of conservation of energy. Total energy must be conserved. Another way that this is sometimes stated is if you have an engine, the maximum efficiency of your engine is 100%. You can only get as much work out as heat you put in. Now let's just reiterate what a heat engine is. A heat engine is just some device that converts thermal energy into mechanical energy. And a heat engine works because heat flows from hot to cold, and some of that is converted to work. Usually, heat engines work in cycles, so in order for them to continuously do work, their total internal energy can't change. So, importantly for a heat engine, delta U is equal to 0. So which of these engines violates the first law of thermodynamics? And we're again going to assume no change in internal energy of the engine. Well, number one, we have 100 joules of energy in, 120 joules out. That's going to be an efficiency of 120%. Let me actually write it down here. So, right off the bat, that violates our first law of thermodynamics. Can't have efficiency more than 100%. Number two, we have 100 joules in, 100 joules out. That does not violate any law of thermodynamics. It's 100% efficiency. Or it doesn't violate the first law of thermodynamics. It does actually violate the second law, we'll find out. Number three, we have 100 joules in, no joules of work out, and 100 joules of waste heat. Well, that's not a very good engine because it's doing no work, but it doesn't violate the first law. And number four, 100 joules in, 25 joules out, 75 joules of waste heat. That is 25% efficient. And that doesn't violate any laws of thermodynamics. This is going to be a more reasonable, accurate engine car engines are going to be on the order of 20% efficient. Okay, so the second law of the thermodynamics is the interesting one, and it's stated in a lot of ways. Here are a few. You can't break even. The house always wins. The randomness of the universe always increases. A perpetual motion machine can't be built. Maximum efficiency is less than 100%, or machines always lose some energy as heat. And there are all kinds of different ways of stating it, but they pretty much mean the same thing. We can't convert all of our input heat energy into work, or anytime we're trying to do work, some energy is going to be lost as heat, so we can't keep things going forever. This is an example of a theoretical perpetual motion machine, where water flows through capillary action up this spigot. It has energy, kinetic energy to keep it moving, and it should continuously flow around and around and around. However, some energy is going to be lost as heat, which will gradually dissipate the energy of our water. Therefore, the water will eventually stop flowing. The motion will stop. One other statement of the second law of thermodynamics is, in an isolated system, the entropy of the universe cannot decrease, or entropy always increases in the universe. But what is entropy? Entropy uses the variable S, and it's a measure of the disorder of a system. And I say disorder in quotes because it's not a very precise definition. It's also a measure of how much energy is unavailable for work. So if we're thinking about molecules, we can think about a system that's solid, liquid, or gas. And if we think about how the molecules are arranged, in our solid, our molecules often form this nice crystalline structure. In a liquid, they don't form this nice crystalline structure. Their distances change over time. They're moving a lot. And in a gas, they're all over the place, moving at really high speeds. So which is more disordered, solid, liquid, or gas? Well, our solid is going to be the most ordered, and our gas is going to be the most disordered. So as we go from solid to gas, we're increasing our entropy. High entropy. And this isn't a super precise definition, but this is generally true. The more disordered your molecules are, the higher the entropy. We can also think of entropy statistically. One definition of entropy is how many ways, which are sometimes called microstates, can I achieve this current state, which is called a macrostate. Like, how many different ways can I organize these molecules to have this particular overall temperature? The more ways you can organize a system to get the same value of overall temperature, the higher the entropy, and the more likely you are to be in that state. So here's a question. How likely is it for all of the air in the room to move to just one side of the room? So normally we have air kind of evenly spread out. We could possibly, in theory, by Newton's laws, it is possible that all of the air goes to just the right side of the room. Now this is a pretty easy question to answer if you've ever been in the room, because this never ever happens. We pretty much never get all of the air moving to one side of the room. That's because all of the air, that's because there are fewer ways for the air to be in this ordered state with with the air only filling up half of the room. So this is a low entropy state. And the air filling up the whole room is a high entropy state. There are a lot of ways we could rearrange the particles on the left so that they basically just fill up the whole room and we wouldn't be able to tell a difference. Now, by the second law of thermodynamics, we always go from low entropy from hot to high. We're never going to go backwards, at least not naturally. at least not spontaneously. It would take a lot of work to get all the air to one side of the room. So here's another example of high versus low entropy. This on the left is a high entropy desk, and here we have a low entropy desk. This desk on the left is very disordered. This desk on the right is very ordered. I could rearrange all of these papers, all of this trash, all of these post-it notes in a lot of ways, and it wouldn't really change the overall state of the desk. It'd still be just as dirty, just as disordered. But there are only a couple different ways I can rearrange the equipment on the right desk and still end up with the same nice, clean desk. So this would be a low entropy desk, and this is a high entropy desk. As we add things will tend to go to a high entropy state, and then you'll have to do work to straighten up the desk and go back to a lower entropy state. There's another statement of the second law with respect to heat engines that says that it is impossible to extract an amount of heat QH from a hot reservoir and use it all to do work W. Some amount of heat must be exhausted to a cold reservoir. Another way of stating this is the efficiency of a heat engine is less than 100% because there's always going to be some waste heat. Another statement of the second law tells us that heat will only spontaneously flow from high temperature to, there should be a 2 here, to lower temperature, and never the other way around. Heat flows from hot to cold. Now it is possible to move heat from low temperature to high temperature. Like you have a refrigerator. That moves heat from low temperature to high temperature to keep things cool. But it takes work to move that heat from cold to hot. It won't happen spontaneously. So which engine cycle violates the second law of thermodynamics? Assume no change in internal energy of the engine. Well, number one, we are 120% efficient, so that definitely violates the second law. Greater than 100% efficiency. Mostly it violates the first law, though. Number two, we have 100% efficiency. 100% of our work, or heat is converted to work. So that violates the second law first. Second law. Our third engine, all of our heat stays as heat. That's 0%. That's just fine by the laws of thermodynamics. It's not a very good engine, though. And our fourth engine, 25% efficient, at least based on what we know, it is just fine. So we mentioned that a refrigerator can move heat energy from low temperature to high temperature, and this is just how a refrigerator works. Basically, we have a compressor in the refrigerator, and it's going to compress some sort of gas, and as you compress that gas, it heats up because we're doing work on it, we're adding energy. Then the coils on the back of the refrigerator let the hot ammonia, the hot gas, dissipate its heat. It releases heat to the energy. And then we send that now newly cool gas through an expansion valve. It's right here at C. So we expand the gas, and as the gas expands, it cools down because it's doing work on the environment. So we have this low temperature gas now, very cold, and then we run it through the inside of the refrigerator. Now that it's lower temperature than the inside of the refrigerator, heat is going to flow into that cold gas and heat it up. We could take that slightly warmer gas, compress it, and then repeat the cycle to dissipate the heat. Air conditioner works in a similar way. We compress some gas, heating it up. Then we dissipate the heat. And as that heat is dissipated, it condenses into a liquid. And the liquid runs through an expansion valve. And it becomes very cold gas. And then that cold gas is used to, or is run along some air. It can absorb heat from the air, and therefore we have cold gas that can be run through the building, cold air that can be run through the building. In all of these cases, we have to do work in order to compress our gas. So we have one last law of thermodynamics, the third law, and it just tells us what happens, how to get to a minimum entropy. It says that the minimum entropy of a substance occurs at absolute zero. Another statement of that is a perfect crystal at absolute zero has zero entropy because it's perfectly ordered. And I think this diagram illustrates it well. At absolute zero, we're going to have essentially no molecular motion, and all of our particles are going to be perfectly organized in this nice, perfect crystal form. As any temperature above absolute zero, our molecules are going to be moving more, and it's going to be a lot more disordered. So, in summary, entropy measures disorder. The Zeroth Law of thermo defines thermal equilibrium and temperature. The first law of thermo is a statement of energy conservation, and it also means that our maximum efficiency of a heat engine is 100%. The second law of thermodynamics tells us that entropy of the universe always increases. Heat always flows from hot to cold, at least spontaneously, or our maximum efficiency is less than 100% in a heat engine. And the third law states that absolute zero is our minimum entropy. That's all for the laws of thermodynamics. Bye.